Right, I'm gonna ignore not ignore, but I'm not gonna read through these so you guys can read. The two ways to find torque on an object. So torque is equal to R perpendicular to F. If it's at an angle, that's RF sine theta, but it's like the same equation. And then torque is also, net torque is equal to I alpha. The equation sheet has it like this, but I just multiply up because I like it in this form better. If you increase the torque applied to an object, then the angular acceleration would increase because of this relationship, right? If you have more torque, you'll have more angular acceleration. The rate that angular speed changes is going to be your angular acceleration because that's what acceleration is, right? The rate that's velocity changes. To find change in angular momentum, first equation is on your equation sheet. And then the second one, if we know L equals I omega, change in L would just be I change in omega. Similar to delta P equals M delta V. Which one has the greatest angular acceleration? So the one that has the greatest torque. Here, this would be 2F and half R, which is like 1 FR. This would be FR plus half R times F, which is like 1.5 FR. This is FR plus half R half F, which is like 1.25 RF. And then this one is just 2F. Probably didn't need to do the math there, right? 2F is the greatest force and is at the greatest distance. Here, this has a force here, but it has the other F at half the distance, so not as much as having 2F at the full distance. This is same force but closer, so not this, and this is less than this. So, asteroid moves in elliptical orbit with the sun at one focus as shown to the right as the asteroid moves from point 2 to point 1. So we are getting closer. That means your I, if you're getting closer, your I is decreasing. Less inertia when you're close, more inertia when you're farther out. What happens to your angular momentum? So there is no external torque on the system, so that's going to stay the same. Angular speed, if L equals I omega, and we know I just decreased and L stays the same, omega must increase. Kinetic energy is 1/2 I omega squared, omega decreased, I decreased, omega increased. Normally that would balance out, but this is squared, so this one actually has a greater effect. So overall it increases in kinetic energy. And if you're increasing kinetic, that had to come from somewhere, and that means you must have lost gravitational potential energy. Pulley, this is actually supposed to be counter. So it's initially moving counterclockwise. So my initial velocity is counterclockwise, which is positive. So if I sketch my angular velocity graph, start positive, and then to find the acceleration, I have to look at the two torques. So I have two torques, both at the same radius to the 5 Newton winds. If we're talking about going up right here, that is clockwise. So my net torque is a clockwise or negative, which means my acceleration will be negative, so it would look something like that. Riding a merry-go-round, spinning around counterclockwise super fast. All of a sudden a volleyball, I forgot I did that. Volleyball comes flying, and I'm so athletic, so I catch it. What happens to the angular momentum of Miss Campbell in the merry-go-round, and what happens to the angular momentum of Miss Campbell, the merry-go-round, and the volleyball? So this is the entire system. If we're talking about the entire system, that's total angular momentum. That is going to be conserved because there's no external torque. Now, if I'm talking about me in the merry-go-round, now the volleyball is external, right? Because I'm not including volleyball. So the volleyball is an external torque, and when I catch it, the volleyball is applying a torque that way, which is against my rotation. So me in the merry-go-round, our angular momentum is going to decrease because the volleyball is exerting an external torque against the Miss Campbell rotation. Or you could think about when I catch it, because it was going against me, I'm going to give some of my momentum away, I'm going to slow down, I'll have less angular momentum. Similar reasoning there. The rod is initially at rest on a frictionless surface, has rotational inertia I, puck of mass m comes in at a distance d. The puck has an angular momentum of mvd with respect to the pivot point. When the puck collides, it rebounds off with a 1/2 v. What is the angular momentum? So this is a collision. I'm going to say angular momentum before equals angular momentum after. Angular momentum before, it tells me, is mvd. It's just the puck, and then after it is both the puck and the rod. And the puck we just said was the mv naught d. Afterwards, think about it. This guy's coming in with mv naught d amount of momentum, and then it turns around and comes back with this. That's the same thing, right? Just half the initial velocity. So half v naught d. Still m and d, right? The where it hits matters. So if I came in right here, that would be less momentum than here because that distance matters. And then I need to take into account direction. So at first this was clockwise. So this guy is negative. This guy's counterclockwise, so it's positive. And then this is the 1/2 mv naught d. Just pull the half out front because it's just a coefficient plus L rod. And I don't even have to substitute in for L rod because I'm looking for it. So then I subtract over. This is 1 mvd minus 1/2 mvd, which is negative 3/2 mv naught d. And there's your answer. If the ball stopped, find the angular velocity. So still L before equals L after, still the same initial setup, but now after is only the rod, which is I omega, and the rod, right, is just called I, so that's good. Get omega by itself, divide I over. Two people are sitting on a uniform seesaw with the fulcrum at the center. The boy is sitting on the left side, and the girl wants to know where she should sit in order to balance out the seesaw. What do we need to know in order to figure out where to sit? So I'm looking for what this distance needs to be. So the idea here is we want to balance torques. So I need the R and the F for each of them. Well, I'm looking for this. So we need this guy's radius and this guy's force. The force is just the force of gravity, so I need his mass. So I need the mass of the boy. You need the distance of the boy from the fulcrum, right? This distance right here, d. And then I also need the mass of the girl. Click the word girl. Mass of the girl, and then I'll be able to find the distance for the girl, because I'll just set the two torques equal to each other. That's RF equals RF. The force is just the force of gravity, mg. So I need the radius of the boy, mass of the boy, radius of the girl, mass of the girl, and then you can rearrange to get the radius of the girl by itself. Solid sphere of mass m has and radius r has a rotational inertia of this. This is rotational inertia of the sphere. It is released from rest at a height h and rolls down without slipping. What is the velocity at the bottom? So we're going to use conservation. That's funny. Conservation of energy. I'm going from all potential. This is rolling, so it has both translational kinetic and rotational kinetic. This is mgh. Translational is 1/2 mv squared. Kinetic, rotational is 1/2 I omega squared. I'm going to take this, I'm going to substitute in for I. And then I need to substitute in for omega. We know that V equals R omega, so omega is V over R. And now I'm going to square. So this is mr squared V squared over R squared. The 2 and the 1/2 cancel out. The R squared over R squared cancels out. So this is just, I'm running out of room. 1/2 mv squared plus, and that's just 1/5 mv squared. Now, these two you can just add in your calculator, or you can make them like terms. Doesn't matter to me. And then the main thing is if you do it in your calculator, you do math enter to get the fraction. So this is mgh equals 7/10 mv squared. M's cancel. Trying to get v by itself, so I need to move the 10 over by multiplying both sides by 10. And then divide the 7 over and take the square root. So the square root of 10 gh over 7, or 10/7 gh. Child on a spinning merry-go-round walks from the center to the outside. What happens to each of these things? So in the center, I walk out, so I'm increasing the rotational inertia. Angular momentum is going to stay, we're talking about of the child and merry-go-round system, so that's going to be the total, so that's going to stay the exact same. Now if it was just the merry-go-round, yeah, that might change, just the child might change, but the whole together, there's no outside torque, so it wouldn't change. Angular speed, so we know that L stays the same, but I have more I, so that means less angular speed, and then kinetic energy is 1/2 I omega squared. More I, less omega, this one wins, right? The squared one wins, so overall it's smaller, so B. I want to know where to put an upward force in order to keep the meter stick in equilibrium. So this is my meter stick, and I have a downward force here. This right here is causing a counterclockwise, so this is a counterclockwise torque. If I want to keep it in equilibrium, you need a clockwise torque. So if I have to push up, right, I could push up here. Oops, sorry, you can see. I could push up on the left side, which is clockwise, or the right side, which is counterclockwise. I need clockwise, so I have to push down on this side and then up on this side. That's what's going to balance out. This and this balance out. This and up here do not balance out. Right, so I know it's going to be on the left side. That crosses off anything H through M. And I need to find exactly where. So it has half the force. So think about if torque equals RF, if I have half the force, then you would need to do something to the radius to balance out to keep the same force. Half the force would be balanced out with twice the radius. Now, twice the radius doesn't mean go 2 notches, right? It means go 2 times farther than before. So at first, this was my original radius, which is 1, 2, 3. So if I'm going to go on the left side, but I want to go twice as far, you go 1, 2, 3, 4, 5, 6. So A would be the answer. And remember, when I'm counting my radius or looking at that distance, it is measured from the center. So however far from the center. 3 twice that is 6 from the center. Where would you put another downward force? So again, still need clockwise torque to counteract this counterclockwise. If I'm going to have downward, if I have a downward on the left side, that causes counter, which doesn't balance out a counter. So if I have it on the right side, see how this is a clockwise? So I definitely want it on the right side, because if you have it like this, right, down and down here, cancel out. And I have 3 times the force, so what am I going to do to R with 3 times the force to balance out? 3 times the force will be 1/3 the radius. So here, this was the original radius. I need to go on this side, but I only want to go 1/3 as far. So if it was 1, 2, 3 tick marks, now 1/3 will only be 1 tick mark, which is H. Again, I went to the right because we decided that downward force needed to be on the right in order to balance out. Alright, I have a mass on my spinning platform. I apply a torque for 5 seconds. I stop it. I move the mass closer to the center of the platform, so that is less I. And I apply the same torque for the same amount of time. How does the angular speed now compare? So think about, I have torque and I have time, which means I'm looking at this equation kind of. So I'm either case, right, same torque, same time, I'm getting the same change in angular momentum. So in either case, right, they gain the same L in both cases. But if they both gain the same L, but one has less omega, or sorry, less I, see how that's more omega? So how does the angular speed compare to before? It is faster now. Even though they both are gaining the same amount of momentum, more momentum, less I is faster. So, which makes sense, right? When we move it closer, it's easier to accelerate. So if I'm still applying the same torque for the same time, but it's easier to accelerate, it will get faster. What could I change in order to make that new system spin at the same angular speed? So I still want the smaller I, right, that closer mass, but now I want the same omega, so L equals I omega. I still want this smaller, but I want this the same, so that means I need less angular momentum. So you need to gain less angular momentum. And if I'm going to gain less angular momentum, well, that came from the torque and the time. So I can either have a smaller torque, or you can apply that torque for less time. Pulley is initially rotating clockwise, so initial velocity is clockwise, which is negative. And I have two forces. This is the bigger force for sure. That is also clockwise. So my net torque is clockwise, which is also negative. So that means I need to start negative and I need to have a negative acceleration. So this one, right, is going to start that way and it's just going to accelerate that way. So just get faster and faster in the direction it's already moving. Different combination of things to get angular acceleration. So I looked at all the equations on my equation sheet that have alpha in it. So I've got this one right here. If I wanted that, I would need omega, omega naught, and time. I also have the change in theta is omega naught t plus 1/2 alpha t squared. So you would need change in theta, omega naught t. I have the third one that's not in the equation sheet, but you can get it from the first three, right, just translating. Omega squared is omega naught squared plus 2 alpha delta theta. So in that case, I would need omega, omega naught, and change in theta. And I could also do my torque equals I alpha, so you would need net torque and I think that's everybody. You could also do like combinations, but I'm just going straight equations that, not using two equations. Alright, disc and hoop are both released from rest and roll down without slipping. Who reaches the bottom first? So the one that reaches the bottom first is the one that has the fastest overall speed. That was the one that has more translational kinetic energy, right? Because translational is the 1/2 mv squared. They're both starting with the same amount of potential energy. So, and we know that potential is going to both translational and rotational. So if I have more translational, that must mean I have less rotational kinetic energy just because it has to share between them. And the one that has less rotational is going to be the one that has a smaller, less I. Less I means mass not far away. Hoop is mass all far away from the center, so disc is the one that has less. Two balls A and B of different masses are stuck on either ends of a thin rod. Student releases the rod by both ends straight up, so they're holding both the ends and then let go at each at the same time. Will the rod rotate as it falls? And if it rotates, what direction? Why or why not? So let's think about. I have it, it's held up, and then it's just released like this. So something only rotates if it's caused by a torque. So this is basically a question, is there a net torque or not? I definitely have two torques right here, right? I have this pulling down and I have this pulling down. This is the heavier mass, so this is definitely a greater force of gravity than this guy's force of gravity. Now, let's think about torque is not just about the force, torque is about RF. So, yes, this guy has a greater force, but I have to look at the R. It's not like the pivot point was given to me, right? It's no like fixed point that it said, hey, it's rotating around this. So when that is the case, when the point is not like a fixed point, it will always rotate around its center of mass. Now remember, its center of mass is not necessarily the dead center, it's the center of the masses. This has a much greater mass, so see how your center of mass would be kind of over on this side? So your center of mass, I don't know exactly where it is, right? But I do know that it's left of center because it's going to be closer to this guy than this guy. Think about if I have this and oops, that didn't work. If I hit it, right, it'll rotate. If I didn't have like a frictioning surface, it would rotate around its center. If I did that to a hammer, the hammer is not going to rotate around this center point, right? It would be closer to the like hammer head side. So that's the idea here. So now I'm looking at my torque. Yes, this guy has a greater force, but it has a smaller radius. So it has a smaller distance, so more force but less R actually balances out to the same torque. So they each have a torque, but they're actually about the same torque, so it cancels out. So if you have like a hammer, right, it's the idea, if you drop a hammer, the hammer doesn't like just rotate with the heavier side. It will just, as long as you let go at the same time on those sides, it will just drop straight